In our lesson 3, we are going to try to understand with more detail what functions are and some aspects and features of functions that you need to know in order to solve some questions. First of all, how do you represent a function? A function, can be represented in many different ways. They all mean the same, okay? This is probably the one I prefer if I'm not to sketch it, okay, if I don't have a y-x axis. And this is probably the one I prefer if I do have a y and x axis. And this, you may see this, I don't use this at all, but you need to understand that all of these mean the same, okay? I particularly like this when we are dealing with numbers because you can see this kind of a math factory in which you plug in numbers in x and you are going to get numbers, other numbers out of this, which are going to be your y values, right? So for example, if you have this particular function, if I throw at it the numbers 1, 2, and 3, I will get the numbers 4, 7, and 12. These are going to be your y numbers, okay? And this can be used to get any type of mapping. Mapping means that you are going to turn any x, which is called the object, into a y, which is the image, all right? So a mapping turns an object into an image by means of a mathematical expression, all right? For example, you have here many different ways now sketched the graphical representation of mappings, but not all of them are functions. The last two, as you can see here with the crosses, they are not functions. And why is that? Because for a mapping to be a function, for every object, you are going to get only one value of y, one image. And this happens over here. For every x, you'll have a y. This will happen over here. For every x, you will have a y. Note that on this particular case, you have two values of x with the same y, but that doesn't matter. This is called a 2-1 mapping, okay? Actually, you may have an infinite number of x's having the same y. If you have a straight line, straight horizontal line, you have an infinite number of x's having the same y, and that is a function, okay? What must not happen is one value of x yielding two values of y. So this is not a function. This is not a function, okay? You'll have to make restrictions over here to allow this to become a function, okay, or over there. So you will only have a function if one object will yield only one image, okay? Other things you need to know, the domain, the ideas of domain and range. The domain is a very simple thing, as well as the range. The domain is the set of all values of x for which a function is defined. So basically all the numbers that you can throw at a function, okay? All the values that are on the horizontal axis that you can use, all right? The domain is defined here on the horizontal axis, x. If you take a function such as 1 over x, you can see that there is one specific number that you can never use, which is 0. 1 over 0 is undefined, right? So what does this mean? This means that the domain of this function in particular can be everything but 0. So you can write it like that, x different from 0. Or you can write it like this, x belongs to the set of real numbers with the exception, that's what this bar means, of 0, of the number 0. For example, if you have f of x equals the square root of x, then here the problem is bigger because x cannot be negative. So how do you write this? You write that the domain is x is positive or 0, it still can be 0. Or you write it like this, this is a subset of the real numbers that includes 0 and is positive. All right? The domain can also be given by external circumstances that do not relate to the mathematical expression itself. So let's say, and I'm from physics, so I just use this example from physics. f of t equals u plus at. This is one of the laws of motion, and your variable, your unknown, is t. U and a are numbers, okay? And t stands for time, okay? So what would be the domain over here? There's no problem in mathematical terms in throwing any number at t, but in physical terms there are, because you have no negative time, okay? So here the domain would be that t is positive or equal to 0, or the subset of real numbers that is positive and includes 0, okay? Just that. What is a range? The range is the set of all possible values of y, okay? So domain, the set of all possible values of x. The range is the set of all possible values of y. And this is the dependent, obviously, on the domain, okay? Because the range comes from the transformation of numbers in the horizontal axis into numbers in the vertical axis, okay? So if you have restrictions in the horizontal axis, that is going to have consequences on the vertical axis. Don't forget, in science, we actually call this the line of the independent variable, and this the line of the dependent variable, because this is dependent on this. So the range is dependent on the domain, okay? Let's see an example. Let me see. Yes, this one has an example. If nothing is said about this function, then the domain is R. X can be anything, right? This is a straight line up. So if the domain is R, the range is also going to be R. There are no restrictions whatsoever in X or Y. But if for some reason I decide that the domain of the function is x bigger or equal to 4, so I'm restricting the values that x can take from 4 onwards, then this is going to have a consequence on the range, because the minimum value that you can get on the y occurs when I just plug the minimum value of x over here. 4 plus 1 is 5, right? So the possible values of y start on 5 and then go up forever, okay? So what is the range of the function? Is y bigger or equal to 5. See here how a change in the domain will cause a change in the range? Let's see another example, in this case with a parabola. If nothing is said over here, x can be anything, right? So the domain is R. But since this is a parabola, and you already know that the parabola has a vertex, either a minimum number value or a maximum value, and in this case the coefficient of x squared is positive, so the parabola is like this, so the vertex will correspond to the minimum value, then you have to consider the y-coordinate of this minimum value, the y-coordinate of the vertex, to figure out what the range is, okay? In this case, the vertex is on point 1, 1, right? So you see here in yellow, the domain can be anything, but here in pink, the range starts in 1, the y-coordinate of the vertex, and then goes up indefinitely. So the range is y bigger or equal to 1. What if I apply the same restriction to this domain that I did over here? If I apply this restriction to this domain, then I'm going to have a change also in the range. What I'm saying is that the minimum value of x that I can use is 4. Okay, so a little bit to the right of the vertex. Okay, so over there. Here I've just drawn the parabola. Okay, but here the dotted line means that this is no longer there. It starts over here. This is supposed to be 4. Okay, so what is going to be the range? You just have to put the coordinate of the x, that is the value 4 over here. So 4 squared is 16 plus 1, 15. So the function will start in 15 and go up, right? Did you understand here how one thing, the domain, is going to influence the range? For some weird reason that I never got, to be honest, some students tend to have problems here with the domain and the range, but that is just this. The domain then the set of numbers that x can take, the range, the set of numbers that y can take, can be. Let's talk now about inverse functions. And by that, and with to start that, I just want you to look at these pairs of lines. If you have y equals 1, what would that be? That would be a vertical line passing through 1, right? If you just say that x is 1, the y doesn't depend on x, so it's just a vertical line. Y equals 1 is going to be a horizontal line that passes on a point 0, 1, right? This one passes on point 1, 0, this passes on point 0, 1. Same thing, but now y equals 3. The straight line passing on point 0, 3. The line x equals 3 is a vertical line passing on point 3, 0. Look now at this one. You have y equals 2x minus 1. So this is a straight line with gradient 2 and y-intercept minus 1. So you have here these 2 points. This one is 1/2 or 0.50, and this is going to be 0 minus 1. What are the points that you would have if you would apply something like this? The 1/2 0 will become 0 1/2, and the 0 minus 1 would become minus 1 0. And then you would draw a straight line that passes over here. If you are to determine the equation of this straight line, this is what you get. Now start looking at the relationship between this and this, which is the same as between these two and those two. One last example. Let's say that you have now this quadratic. This is going to be an inverse parabola that passes on points 2, 0, minus 2, 0, and 0, 4. So let's plot these points again, but using this transformation that we just did. So the minus 2, 0 becomes 0 minus 2. The 2, 0 becomes 0, 2. And the 0, 4 becomes 4, 0. And then, if you try to redraw the parabola, this is what you would get. If you try to get the equation of this line, this is what you would get. Okay? The positive square root of 4 minus x would give this part over here. The negative would get this part over here. Okay? So the question is, how do you going from here to here and from here to here? That's obvious, right? But how do you go from here to here and from here to here? You will have to, and I'll go there straight, and I'll talk about this. You'll have to follow these rules. So first one, write the function in the form y equals f of x. Okay? For example, if you have the function expressed like this, just write y equals 2x minus 1. Then substitute, put x as a subject, solve it for x. Okay? So in this case, this will be x. And the final step, substitute y for x and x for f minus 1 of x. So your x will become f minus 1 of x, and this is how you represent the inverse function. And then your y will turn into an x. And this is how you get these expressions over here. Needless to say that if you would apply that set of instructions to these, you would get these back. Okay? Now, pay attention also to what happens graphically. If you know the sketch of one of them, the sketch of the inverse function is going to be, and look over here. I'm just plotting now these two on the same place. The other two on the same place. So all these 8 sketches that I had there, now you only have 4. And for all of them, one of the lines is the reflection on the line y equals x of the L1. Okay? So the reflection of this line on line y equals x is this. The reflection of this line on line y equals x is this, and so forth. So if you know the sketch of a given function, you can almost immediately represent the inverse function by drawing the line y equals x. That's very easy. And then trying to do the reflection of the first on that line. And the outcome is going to be the sketching of the inverse function. Okay? Let me see if there is anything else to talk about this. One important thing. Sometimes the inverse function may not be a function at all, okay? For example, over here, this is not a function, and the reason is obvious. The mapping over here is 1, 2 for most, with the exception of the vertex, to most of its elements. Another thing is that the domain of one function will turn into the range of the inverse, and the range of a function will become the domain of the inverse because they actually invert positions. All right? What about composite functions? Let's say that you have two functions, f of x and g of x. F of x equals u, and u may be whatever mathematical expression. And g of x equals v. And again, v can be any mathematical expression. So f of x plus g of x, if you add these two, is as simple as putting the two mathematical expressions, adding one to the other. Same thing goes with a subtraction. Okay? What if you multiply them or divide them? Well, just do whatever the operation is, but now with a mathematical expression. Okay? Here I use the example x squared and 1 over x. So x squared is f of x, and 1 over x is g of x. So f of x plus g of x is these two added. Okay? I just left it like that. Subtracted is this. Multiplied, they just yield x. And divided, they just yield x cubed. What about this? What if you have f g of x? Or the way I prefer it, f, then open square brackets, g of x. This is actually very simple if you practice with a few questions. What does this mean? Let's look first. I prefer using the example because this makes much more sense to teach with an example. What is f of x? What does this do? This turns any x to its square value, right? That's what f does. What does f of g of x do? Now, instead of having here x, you have g of x. And what is g of x? Is 1 over x. So this is what you have, right? This is the original function. Now you have what? You have f of 1 over x, not f of x. Okay? So what is f doing in the first place? Is squaring whatever you have here. Okay? In this case, you had x, so the x is being squared. Now what you have? You have 1 over x. So what's going to happen? The 1 over x itself is going to be squared, and this yields this. Make sense? Note that most of the times, f of g of x is different from g of f of x. Not in this case, though, it will give the same result, but most of the times is not going to be the same. Most important is for you to understand what this means, okay? So you are no longer doing whatever the mapping that f produces on x only. You are doing that mapping on another function that has itself a mathematical expression. So you are going to apply the function or the mapping of f not to x, but to a mathematical expression, which in this case was just 1 over x. Again, I have a few examples in my exercise lessons, so take a look at them for you to gradually understand how this works and to grow in complexity about questions about composite functions. You may have an infinite number of composite functions. I never saw in an exam any more than 3. Okay. Note one thing, very important. The range of the second function needs to be contained in the domain of the first. Why is that? Think of the function g of x. It has its whatever domain, okay? And this domain is going to yield a range for the function g. But now this g of x is going to be what f is trying to transform. So the possible values that g of x can take, which is the range of g, is going to be now the domain of f. And it doesn't make sense that the range of this is bigger than the domain of this function over here. Let's look at an example. Let's say that f of x is square root of x and g of x is 16 minus x. Okay? Let's now look at the domain and the range of each one of these functions. The domain of this function is obviously I made a mistake. This is plus as well. I'm going to change that now before I forget. The domain of function f is, I have to do it. I cannot do it over here. I have to do it in the computer. But this is obviously R0 plus, okay? This cannot be negative. And the range is also the same, all right? For this function, x can take any value, and the range also can be any value. But if I try to do f of g of x, what am I going to have? Now, instead of having f of x, I'm going to have f of g of x, which is 16 minus x. So here inside the square root, and what f is doing is just square rooting whatever I have there. And what I have there now is 16 minus x. So I have square root of 16 minus x. But the range of g, which is r, is smaller than the domain of f. Okay, in this case I put r, but to be honest, this is this, all right, r0 plus. So what do I have to do? I have to impose a restriction to the range of this. This, although technically speaking, g of x, for all that matters, this can take any value, including negative numbers. If I want to plug it over here and make a composite function out of it, I have to restrict this only to positive numbers. Okay? I originally had a range that was bigger than the domain of the main function. Okay, so I have to bring it down, make it just as big as the domain if I want to be able to apply the composite function.